Hi ladies and gentlemen, welcome to lesson 36. We're going to proceed here in a manner similar to what we did last time. I just want to walk through the material here. I also have up on the right hand side a picture of the graph, which as it turns out is really not very accurate, and I just want to talk about that and make sure that nobody's confused and that we're straightforward on everything that's going on. So the first topic here has to do with finite differences for first order derivatives. And you've already seen this before. This is how we developed Euler's method for ODEs. And what I want to do is just talk, I'm not going to go through any of this material. The forward difference, backward difference, and central differences are all straightforward and stuff that's well covered in the book. Or in the sheet here. I just want to talk about the inaccuracy of the graphic that we have, which some of you may have noticed. I just don't want anybody to be confused. So, of course, the big issue is the fact that this value here is really f at xi plus 1, right? That's where the function evaluates at x equals I plus 1. Similarly, down here, this is the function value f at xi minus 1. The values that are given here in the graphic are associated with the tangent line approximation at the point x sub I. And so we're not really interested in that information. That's not what we're talking about here. What we're talking about are the secant lines, and you remember this from calculus, right? We have a secant line that goes through those 2 points, which gives us an approximation for the slope right there. And that, of course, is the forward difference because we're going forward from x sub I. Or there's another approximation that is the secant line that goes through these points, and that secant line is the backward difference because we're backward from where we were, or where we are right here, which is our current point x sub I. And so the way we do, and I'll do the backward difference since that one's less familiar to you. So an approximation for the derivative at x is to say, well, I have f at xi minus f at xi minus 1 divided by xi minus xi minus 1. It's just a slope calculation. That's all the derivative is. And we write this in shorthand. This piece here, we've just agreed, since we know x is the independent variable, we know that f sub I, or we're going to define f sub I, to be f evaluated at x sub I, just so we don't have to write this longer form. And we're going to subtract from that f evaluated at x I minus 1. And that's what that notation represents. And of course, as long as the steps along the x-axis are equally spaced, this is some fixed value, which we generally call delta x. And so this is just our slope approximation from the backwards direction here. And of course, if I average the forward slope and the backward slope, that's really tantamount to drawing a line that is secant through both of those. And you can see just from my crude drawing here, that is a much better approximation to the actual slope at x sub I than either the forward or backward difference. And so that central difference, which I'll write in the shorthand version, the central difference is more accurate. So the derivative is approximately fi minus fi minus 1. Sorry, this is fi plus 1. So we're out here taking this front point, and we're subtracting from it this back value here. So we're taking this rise, and we're dividing it by the run, which in this case is 2 delta x's. And that is our improved approximation for slope. That's the central difference. So this idea of different qualities of approximation for the different derivatives is absolutely critical to numerical analysis. And we'll talk about that some more when I show you how these things are actually developed. The pictures are nice and they're quite intuitive and they refer back to the material that you learned when you were in calculus. However, when we build not only these approximations but more advanced approximations, this is not how we do it. So for the second derivative, the kernel does a nice job of going through the way we actually do things, which is using Taylor's theorem in order to generate approximations. So we have the forward and backward approximations. I've represented these using all three of the different notations that the kernel used, but I will tell you that this is the one that we want to use. So this, of course, is exactly the same as this one. It's just a little bit of shorthand notation, just to make things a little bit tidier. We know the i's go with the x independent variables. We know the j's go with the t independent variables. So when I see this term, for example, I know that it's the x independent variable, but at I minus 1 for its position. And then the t sub j that's where the j represents, is that t sub j. We definitely want to avoid this functional representation here. This is wonderful for calculus. It serves no purpose for numerical methods. Here's what our central difference looks like for the first derivative, and then this is the central difference for the second derivative. And these are both second order approximations having to do with the quality of the approximation. And really what that term comes from is the error associated with Taylor's theorem, which I'll talk about in just a little bit. Finally, how do we put all of this together to discretize and approximate the heat equation? So this is really the topic. This is what we're talking about. How are we going to take this information regarding derivatives and use it to help us do these approximations? So what we've learned already, we could do a forward difference, we could do a backward difference, or we could do a central difference here. And for the uxx, we have a central difference. That doesn't mean we couldn't do a forward or a backward difference, and in fact those exist. But all that we're talking about and all that we're going to use in this course is a central difference for uxx. And looking then at exercise number 4, this really is getting us ready for the wave equation, where we're now going to have a second derivative with respect to t and a second derivative with respect to x. So of course it's no different. It's just doing the partial derivative approximation on the t variable instead of the x variable. But the mechanics are all the same, and I can tell just by looking at this representation here, because I have j plus 1 and j minus 1, that my partial derivatives are on the t variable because the j's are associated with the t. We already set that up as part of our notation when we started. Couple of solutions here, and now what I really want to do is start tearing into the material that we have for forward and backward and central differences as it relates specifically to the heat equation. So the forward difference here is exactly the same as what I had up in the first session. And listen, I know probably what you did in section number 1 was just write down the more standard items for first derivatives, right, using the f's just like we did in that other one. So f prime is approximately, now if I do the forward difference, it's fi plus 1 minus fi over delta x. That's the forward difference, and that's fine. I wanted to do it with the partial derivatives because that's what we're doing in this course, and it's exactly the same. There's nothing that's different. It's exactly like partial derivatives in vector calculus. The way we do that is by holding all the other independent variables as constants. We do the same thing in numerical methods. There's nothing different here. So this partial with respect to x, I can see it's I plus 1 minus u at I, and so it's a partial derivative with respect to x. The j's haven't changed at all. Similarly, then we have the second derivative for utt, and we already went through that. It's the same as what we had, except the difference now is in the j's instead of the i's, so we know it's a partial with respect to t and not x. Obviously the delta t is a huge giveaway as well. So this last question is, how can we tell if a term in part C is for the next time step? Well, so this gets down to looking at the grid that we're going to do our calculations on. And that's a huge part of what I want to show you today, is to help you build the right mental framework to be able to program the numerical methods. So of course, if it's subscript j plus 1, that means it's at time t sub j plus 1. That's the future time. That's the next time from where we are right now. So taking a look at the 1D heat equation, we have the finite differences. So we have this forward difference that we're going to use for the first derivative, and we have a central difference that we're going to use for the second derivative. So, and again, I wouldn't use this function notation. I just threw this up here in case you did, to make sure that you could check your work, but that's not useful to us when we program these numerical methods. You definitely want to adapt this form here with the subscripts, because the subscripts, and when you see the grid, all of that relates to how you're going to program these methods. So the problem with this is actually a really grotesque way of trying to approximate the heat equation. And let me explain why. So we have a forward difference for T. So we have ui j plus 1, and I'm going to write this up. So this is our approximation for the heat equation, and the problem with this is the approximation for the first partial with respect to T. This is what we call an order 1 approximation. This approximation for delta x is an order 2 approximation. We try really hard when we create numerical methods to make sure that all the derivatives have the same order. So this is going to be a problem. Now, this is what you're going to program, and that's fine. I'm just telling you that in reality, no one would do it this way because of the mismatch of orders. So what I wanted to demonstrate for you is how, or at least a way in which this would actually be done. And that has to do with this equation that I've put down over here, where I've replaced the forward difference approximation with a second order approximation. Before we talk about this though, let's take a look at the central difference. So this is our central difference for the partial derivative with respect to t. Now, this has a huge advantage over the system we have above there, because this is a second order approximation to the first partial with respect to t. And this is a second order approximation to uxx. These now match. So it's a very fair question. Why don't we do it this way? It turns out when we go to solve this, and I'm not going to write the whole thing out, but I have uij plus 1, that's definitely the next term I'm interested in, is equal to 2 delta t k over delta x squared times all of these parts here, and then plus a ui j minus 1, because I've added this piece over to this side. So you wouldn't know this necessarily, but this is called leapfrogging, where I go to calculate j plus 1 based upon j minus 1. And leapfrogging methods are inherently unstable. There are no values for delta t and delta x that I can pick that will make this calculate in a stable manner. So while the orders are good, the reason this is not used is because it is unstable. So what I've done is demonstrated a different way of calculating a second order approximation to the first derivative. That's what this thing is here. So let me just write this down for a second. All right. This item here is another approximation to the first derivative. I'm going to show you where it comes from. I'm going to show you how these things are actually done. This is also a second order approximation for the first derivative, and in this case the first partial with respect to t. This is still a second order approximation for the second partial with respect to x. These two things match up. That's good. If we were to solve this out, which I've done in this next line here, we end up with, sorry, this one down here, we end up with something that you can see includes information about the previous time step. It does not just skip. So it doesn't do the leapfrog. And as a result, we preserve that higher accuracy. And it's now a fully second order approximation, and we have better stability criteria. So we'll talk a little bit more about that. The reason I'm introducing it now is because as we move through this particular homework problem, we're going to start to talk about stability. Next thing we're going to talk about here is in part B, just rewriting our approximations in the format that we can actually program for success. So in this case, I have it written this way, which matches with the factors that the kernel wanted us to identify in part C. I would argue that it's probably just as easy and certainly more straightforward to simply write it in this manner here, where we've solved by multiplying both sides of the equation by delta t and then adding over uij. And of course, if you did it with the representation, the function representation, which hopefully this will be the last time you do that, but if you did, the answers are up here. So this moves us to part C then, and this question about why do we care what these factors are. And listen, there's no way I expected that you would get this, to be quite frank about it. Unless you've done some numerical methods programming before, you wouldn't really understand how important stability is. And it turns out that these factors are related to the stability of the equation. And all I've done here is just provide you, it's not a proof by any means, and it's really kind of a lukewarm explanation, but hopefully to give you a little bit of an idea of why this is the thing that we're going to consider. And you notice, I mean, even up here in this factor, it isn't the whole factor we care about, it's really just this second half. So ultimately, all we really care about is this item here. What is k delta t divided by delta x squared? What is that value? So if that value is about 1/2, and then we go and plug it into our approximation for the temperature, we end up with this result here. And what do you notice about this result? Well, I'm calculating some value I using I plus 1 and I minus 1. It looks a little bit like that leapfrog that we were talking about with the j's. And sure enough, this is unstable. Anytime that I lose that input from the previous value, then I start to have some serious stability concerns. And it turns out for this particular implementation of the finite differences for the heat equation, if this factor is greater than 1/2, we lose stability. We will not be able to do the calculation. So regardless of accuracy, no matter how small we pick delta x and delta t, this is not a question of accuracy. We could pick delta x and delta t to be 10 to the minus 10, 10 to the minus 12. If this relationship exceeds 1/2, the calculation will blow up. It is unstable. Looking at this second order version, where I took and replaced that partial with respect to t approximation with something that was second order instead of just the first order forward difference, we end up with a situation that looks like this one here. And we can still see that important factor in there, k times delta t divided by delta x squared. But in this case, what you notice is this central term does not vanish until k delta t over delta x squared is approximately 1. And so this formulation is not only more accurate because both halves are second order and it's not a mix of two different orders, but it's also more stable because we expand the set of values in this k delta t over delta x squared factor that we can endure. So again, that's just FYI. This whole question, part C, was about stability. Just to let you know, if you're doing one of these approximations, just because your answer blows up doesn't mean necessarily that you've done it incorrectly. Finally then, we have 36.3, which is the introduction to the wave equation and how we would do this for the wave equation. And in this situation, again, I wrote the function part down. I'm not going to spend any time on that. With the subscripts for the i's and j's, I is still associated with x, J is still associated with T, and we put a second order central difference in. So in this situation, we're better off. Both of these approximations are second order, and when we solve this out, we think that our stability will probably be reasonably good, although we have to consider values that we can endure. But we'll take a look at that in part B. So in part B, we're going to solve for the next time step, and solving for the next time step in a very straightforward manner gives us this. Rewriting to kind of identify that stability factor, which in this case has a delta t squared in the numerator instead of delta t, then looking at this central term, it looks like we might be able to tolerate that value of c squared delta t squared over delta x squared, anything underneath 1. That's just conjecture. I don't actually know the answer to this question. I don't know if that's good, if the stability is good up to that or not, but that would be my initial guess, is that we're probably good up to 1. So that concludes the portion on the pre-class material. For the scoring, this last problem's worth 2 points, 1 point per part, and then the first and second problems are 3 points apiece. So for the first problem, remember we talked about, making sure you watch the video and then taking a look to make sure that you have the ability to write down these different representations for the derivatives, and then of course always understanding what the i's and j's are related to and what they mean with respect to position and time. And the middle problem here, this is where we do the full up heat equation, and we come up with this representation here. And this is the one you're going to end up programming. You're not going to end up programming mine unless you already have something successful here and you want to try something different. And the reason that we do that, I'm just letting you know, the reason that we do this is to match up the accuracy, so that the accuracy for the first partial with respect to t and the second partial with respect to x are both order 2. Has nothing to do with stability. It just turns out we get a little bit better stability criteria, and we get that for free. And that's what the part C conversation is about. You don't need to know this in depth. You just need to know you should always be checking this value. K times delta t over delta x squared is something you should print out every time, print it out to the screen every time to make sure that value is underneath 1/2. All right, I'm going to pause here and then move to the second part. All right, where do these approximations really come from? Bottom line is they all spawn from Taylor's theorem. So let me orient you. We are expanding about x. So you're used to calling this x naught, but we're just calling it x, and that's why x is in every one of the derivatives. That's the point around which we are expanding. So we are expanding about this point, and then we are approximating away from that point down the number line. And what we're looking at is the distance h down the number line. So we're going to move a distance of h down the number line. If we do that, then our current value, our x naught value, if you will, is x, and then the value we're looking to approximate at is x plus h. And when we take x plus h minus x, of course we end up with a bunch of h's. And so we have this baseline representation, which is Taylor's theorem expanded about the point x, where we are approximating at the value x plus h. So we're somewhere down here, we're at x plus h, and that's where we're approximating the function. So how do we use this to come up with all of these numerical methods? Well, start with a couple simple examples that will make sense for you. Let h be delta x. So I'm just going to substitute straight in. Always, I'm just going to substitute straight into this representation that I circled here. I'll circle it again, it's so important. This is the representation of Taylor's theorem where we've expanded the function about the point x and we are evaluating at x plus h. So let h be delta x, make those substitutions, and what we're going to do is we're going to grab an approximation for f prime. So when we solve this approximation for f prime, and let me add a little bit more in here. I have f prime times delta x is what I've solved for, And that's equal to f of x plus delta x minus, I subtracted the f of x over there, but it's also minus a delta x squared over 2 f double prime of x minus other things. Divide both sides by delta x. We end up with something that looks like this, but then I'd have a minus delta x over 2 f double prime of x, etc. This is why the forward difference approximation, which is what this is order 1, because I have an order delta x accuracy. My error is going to be on the scale of delta x, and that is delta x to the first power, so we call this order 1. For the backward difference, what I'm going to do is use the same representation from Taylor's theorem, but h is going to be negative delta x instead of positive. So I put a negative delta x in, negative delta x squared, negative delta x cubed, etc. Same thing, we're going to do the first derivative, the approximation for the first derivative. Notice again that I would have, solving for negative, I've solved for negative delta x f prime, and this would give me a negative delta x squared over 2 f double prime plus blah blah blah. And when I solve, dividing through by delta x, I'd have a negative delta x over 2 f double prime of x minus or plus other material, I don't care. Notice the first term has order delta x, which is order 1, because we're looking at the power of delta x, the exponent. So it's an order 1. Now what happens if we want to use both of these approximations? So I have an approximation at h equals delta x and at h equals negative delta x. And what we're going to do is we're going to take a linear combination of those two approximations, and we're going to scale them. So we're going to scale the first equation by q1 and the second equation by q2, and we're going to do it in a very purposeful manner. What our goal is to make the coefficient in front of f prime be equal to delta x, and to make the coefficient in front of f double prime be 0. We want the error to be out here in the delta x cubed range so that we have a better order approximation. So we want to kill off this delta x squared error, which is what's giving us this order 1. Remember, this delta x is because we divided by delta x. So this is really delta x squared over delta x. Well, this is just linear algebra. We can do this. We look at the first equation is going to be the f prime equation. So I've got 1 times q1 minus 1 times q2 equals 1. They're all multiplied by delta x. So I have that equation. This is my f prime equation right here. This is the f prime equation. And then this is my f double prime equation, where I have 1/2 times q1 plus 1/2 times q2. And of course they have delta x's squareds in there, but since it's equal to 0, I can just divide the delta x squareds out. And we can solve for this. And what this gives us, when we multiply the top equation by 1/2 and the second equation by negative 1/2, and then add those two equations together, we end up with 1/2 f at x plus delta x minus 1/2 at f of x minus delta x. And then the f of x terms just happen to cancel. We weren't going for that, but that's just the way it turned out. And we ended up with a delta x in front of f prime of x. That's what we wanted. And most importantly, we got the delta x squared terms to cancel out and become 0. And that gives us a delta x cubed over here. Well, solving this equation for f prime, we write f prime is equal to, and it's these two items, and then I'm going to subtract all of this other stuff over here. And this is the approximation I'm after, and this is really an approximation here. What does this look like? This is the central difference approximation. The central difference approximation cancels out the delta x squared terms to give me an error, which is now delta x cubed divided by delta x, and this is order 2. So it's not order 2 as in it's twice as good. It is a power of 2. So if delta x is 1/100th, the error here is in the range of 1/10,000th. Much, much better than a forward or backward difference. Okay, so sure, nothing exciting so far. We came up with central difference. Let's do this again. This time, however, instead of using h as delta x and negative delta x, I'm going to use h as negative delta x and negative 2 delta x. So let me just draw a schematic of what it is that we're going to do. We have x and then xi minus 1, which remember is x minus delta x. This is xi, and then I have xi minus 2, which is just x minus 2 delta x. And what we're going to do, instead of using this front value up here, we're going to use these three function values to approximate the derivative up here. So applying again Taylor's theorem with the h's, we replace the h's and we come up with these two representations for Taylor's theorem. Again, we'll multiply the top one by q1 and the bottom one by q2. And now we want to think about what is our goal. Well, it's exactly the same as it was before. We want the derivative terms to be have a coefficient of delta x, and we want the delta x squared terms, the second derivative terms, to cancel out and be 0. That gives us the following. We have negative 1 q1 minus 2 q2 equals 1. That's f prime again. So again, this is the f prime equation. And then the f double prime equation here, we have 1/2 times q1 plus 2 times q2 equals 0. Solving, we get a negative 2 and a 1/2. Applying the negative 2 to the first equation and the 1/2 to the second equation, we end up with exactly what we want. However, the f of x terms don't cancel this time, which is fine. We have information about f of x, so we don't care. We get our correct coefficient. We have our delta x here in front of f prime. And we get the f double prime term to cancel. So what we have left over is a delta x cubed term, which is going to give us, again, when we solve for f prime, it's going to give us this representation here, and it's order 2. Well, doesn't this look familiar? 3/2, negative 2, 1/2. Looking at what we had here, right, for our accurate approximation, it's 3/2. Whoops, sorry, let me get to it. Right here, 3/2, negative 2, 1/2. So I have applied this approximation for the derivative, which is a second order approximation instead of a first order approximation, to get a more accurate answer, and to make sure that both the delta t, or sorry, the partial with respect to t and the partial with respect to x match up, and they're both second order for accuracy. So this is how it's done. And you can see if I went farther back, if I kept more points going backwards, I could increase the accuracy. All right, let's talk a little bit about programming. Here's what I recommend you do for the programming. I recommend you draw this picture and that you understand it. So what we are doing is we are trying to solve the heat equation. Now, you're not going to do the implementation that I just explained. I just wanted to explain to you how we use Taylor's theorem to come up with all of these approximations, even the simple ones. So this is our approximation where we have a forward difference in t, and we have a central difference for x. So u partial with respect to t forward, second partial of u with respect to x central. Writing this out exactly as you did in the homework, we come up with this situation here, and we see that the uij plus 1 value is based upon these 4 values. And the question is, what? Well, it turns out there's only 3 values, right? It turns out that there's this value at I plus 1j. There's this value at I minus 1j. And then in the middle and over there, I have u at ij. I'm using these three pieces of information in order to make the calculation right here, in order to make this approximation. So when you program, this is the idea. I recommend you draw this grid. Okay? Your solution is going to contain however many values going this way, however many values going in t. Now notice I started my numbers. The kernel started hers with 0 and went to n. I started at 1 because MATLAB starts its indexing at 1. It's just one of those things you have to keep track of. In this case, we are going to set the first set of t values for all the x values equal to the initial condition. And then we're going to set for the first x value and all the t values in that matrix. So now you're starting to see it. You're going to have a solution matrix. And in that solution matrix, you can pick the rows and columns to be whichever way you want. I prefer to have x across the columns because it matches my picture. So this is for the first t value, and this is all the x values across like this. And so we're going to put the initial condition right in here, which I've designated in purple. So the initial condition is going to go right in here. And then I'm going to have, I don't have my orange, so I'll use red. The boundary conditions for all values of t, I have these are the boundary conditions, and they're never going to change. And these for all values of t are also boundary conditions. So what I'm left doing now is filling in the rest of these values. And every one of these values corresponds with a grid point. That's why we're doing the white part. So, and you will do this in a set of loops. So this value here, this calculation, is based upon, just as we saw over here, it's based upon this, this, and this one. And then we calculate the next value, and it's based upon this one, and this one, all according to this formula here. Then I move over and calculate this one, which is based upon this, this, and this, etc. And when I get over here, remember I'm not going to calculate that one, that's a boundary condition, so I'm leaving that. That one is based upon these conditions here. Then I move up to the next row, or however you set it up, columns or rows, and that value, this one right here, is based upon these three values. And then I just march my way across, and then I come back to the next row, march my way across. That's the idea. It never ever hurts to draw this stuff out by hand, do a couple of calculations by hand, do some basic problems to help build the intuition about how this is going to work. Right? Anyway, good luck with your programming over the next couple of days.